Okay, I hope everybody can hear me. Thank you to come to my talk. I'm not used to talk to that many people. That's the first time for me. Usually I'm teaching and students are not that diligent. I'm going to present work that I have been doing in Purdue University with my advisor, Tiark Rompf. Just a small introduction. Purdue University is a university in Indiana, so it's very pretty during the summer and very cold during the winter. If you fly around the United States, it's between Chicago and Indianapolis. So we're here today to talk about Spark and the work we do with it. So in 2011, Spark was a new thing, and it was this new data system that was faster than Hadoop and much more user-friendly. So it was using in-memory instead of disk. And it started as a collection of Scala library, but then it completely evolved to a much bigger ecosystem, and it's ended up to be a complete database system. So now there is a Catalyst, which is a database optimizer, and it also that do code generation at runtime. So based on the query that the user requests, some code is going to be generated to improve performance. And in addition to this performance, there is also the RDD layer, which allows the program to recompute some computation if one of the nodes on the cluster have failed, or if the computation failed somewhere. And one of the also very great aspect is the user-friendly for Spark. Spark is implemented in high-level language in Scala and can be used with multiple different front end, and that has given a huge boost to its usage. So we are mainly focused on performance during my talk. So how fast is Spark, right? We want to know Spark is supposed to improve on top of other database systems. So how fast it is, and can we do better? So first, we are going to look at a very simple data set, which is a data set composed of name that has been happening in books, so over the age, like in 1800. And we are going to do some simple demo to start. So I hope the font is big enough for everyone to see. So here I'm just going to start Spark with Flare support. So like Flare, at the same time that Spark is implemented in Scala, we can easily interface both of them by adding the correct jar file in the middle. So I create a small script that I'm going to run to avoid, but just to show you what I did. I precise where the file is in my computer. I precise the schema, and I'm saving that data set as a temporary table. So if I go here and I just load the demo file, so we are going to create the data frame, and then we will be able to use it. So we can do some easy computation as first. So I have my gbook data frame, and I can do a filter on a word, for example. So I have a column word, and I want to get all the ones that are argument, like at how many times in each year and all of that. So the file that we are using is almost 2 gigabytes, and we know that Spark is pretty fast. So how much time do you think this kind of query is going to take to go through the file and extract all the information? Guess? 4 seconds. So let's hope. And okay, so here first nothing happened, right? Because we know that Spark is a deferred API. So here we are building a graph that is going to represent the computation we want to do, and unless we actually ask an operation that requires I/O, nothing is going to happen. So I have a small function that's going to just compute how long it's going to take. So show is going to give us a result. So let's see how it goes. So there is some bootstrapping, and then at one point we will have a kind of a bar that tells us, okay, like here the stage 1 is being executed, right? So the query plan has multiple stages, and each of these stages are actually going to be generated in Scala in Java by Spark and going to be executed. And so I think it has been a little bit more than 4 seconds for now. So we are waiting. So we have to think what are the overhead happening at that time. So the data is in a CSV file, right? So we have to go and decode each of the column in our file, and then execute the filter. So like there is multiple stages, also the data needs to be somehow transferred between the stages. Okay. So most of my talk is about a demo waiting for Spark to actually give us a result. It should not take much longer now, hopefully. And so what we are going to show is that Flare that we are implemented can do much better. And then by overpassing every aspect that I just talked about, like the different stages, okay, so 91 seconds. And so Flare we see it as an accelerator for Spark, so we are given any data frame, Flare is going to be able to accelerate it. So later on, we are going to see how it is done. So Flare df is going to transform df into a Flare frame, and then we can do the exact same operation that we were doing before. So here, Flare will have 2 steps. So first, it's going to tell us that it took 600 milliseconds to actually generate the code that's going to be executed. And now the code is executed, and it took the 4 seconds that you were expecting before. So it was a good guess, not for the correct question. Excuse me? No. I can rerun the executable that has been generated directly. It's completely outside of the GVM. So here we can say that it's a very simple operation. But so, for example, I have another query called TPCH6 that is doing a little bit more. And if we do this, if we can look how it's going to do. So like Spark also give us an SQL frontend. We can directly create a data frame from an SQL query. So I'm just going to do the Flare one, because we don't want to spend too much time. And up. So before like that, it won't be cached. And so the size of the data is also the same. Like right now, we are using a 1 gigabyte file. And if I use Spark, we can go and see later how long it's going to take. So here we have seen the architecture of Spark, and here, like Flare is completely transparent for the user, right? We are still using the same high-level interface. So what we did with Flare is just we extract the query plan that has been optimized by Catalyst, because every time we build the data frame, we actually build just the plan, and then it's optimized. We take that plan, and Flare is exporting that to a low-level C code that is then compiled and run. And part of the talk today is also about TensorFlow that we are going to see in the second stage. But for now, we are just focusing on SQL query for now. So let's see what happened on our side. Well, it took 41 seconds to run the code on Spark. And it was 3.5 on Flare. So let's see a wider range of results. Here I show you just 1 or 2 queries. And so the TPCH benchmark that we are using is an industry standard benchmark that is using multiple SQL operations like aggregate, anti-join, semi-join, group by. And we compare 4 different database systems. So we use one which is more like a traditional database system, Postgres, Spark, Hyper, which is the state-of-the-art in terms of database system, and Flare. So Here the scale it's a log scale, so we have to be careful, but every time we have an increment of order of magnitude between the scale. And so we can see that we have two kinds of systems. There is Spark and Postgres that are having kind of slow performance, and Spark and Hyper and Flare that are doing very good for almost all of the query. And while Postgres do not have any code compilation like Spark and Flare or Hyper, they are doing almost the same that Spark on all the queries. So now the question is why all the Spark cannot do much better by removing most of the overhead. And so that's why we try to achieve by using Flare. And another aspect of the system is loading the data. So most of the time, we only talk about the computation performances, but the data loading matters as well. And so here we look at Flare and Spark using two different formats, the CSV format and the Parquet format, because the Parquet format allows us to load less data in memory, like we can only load certain columns if we want. And we see that by generating very specialized low-level code, Flare in CSV is actually faster than Spark using Parquet. So while Spark is generating code, it's still having some generic code to load data, which make all of the dispatch method in the JVM needs to be executed almost at every step of every record, right? So when doing a CSV, some method have to be called for every character, which make a huge overhead at the end. Whereas with Flare, we actually generate a low-level code. Like if we know that our table has one integer and one double, we know that we have to parse an integer and then a double. We don't have to dispatch on the fly. And so Flare allows us to increase performance on different paths, like on the computation aspect and on the data loading aspect, which makes that at the end, it end up to we end up to have a performance very close to very low level C code that we could write to just execute the given query that was given to us. And so here we were focusing on only one thread performances. So now we know that Spark is also built for distributed system and parallelism, so we need to look to that as well. And we did some experiments. So here I picked out 4 different queries within the benchmark, and we run them in parallel. So the machine we are using is a 4-socket with 18 cores on each socket, and each socket has access as 256 gigabytes of memory. So we see that if we look at Spark, which is on the upper right corner, that's pretty good scale up, right? For each time we multiply by 2 the number of threads, the performance are not totally linear because there is some overhead, but it's doing pretty well. We see that there is a small decrease of performance between 16 and 32 threads. So any idea why that could happen? So like we have 18 cores, when we want to use 32 threads, we have to use 2 different sockets. And if we load the data on a given socket, every thread on the other one will have much more overhead to actually access the data. So when we do that, we have to remember that, well, the machine is not a uniform access, right? So it's a NUMA machine, and that needs to be taken in account when we generate code. And so the benchmark I just showed you, we don't yet have enabled the optimization for NUMA-aware architecture. But if we take some example like Q1 and Q6, which are simple query, and we try to generate code based on the number of sockets that we are using. So just to explain a little bit the graphic that has a lot of things to do, the light blue is when we try to use only one socket. So for 1 and 18 cores, we can put all the thread on one socket. And so we see that for we get pretty good speed up. We get around 12 speed up for Q1 and around 14 speed up for Q6. And now when we go to 2 sockets for 18 core, we realize that for Q1 it doesn't change much, right? So if we still have 9 threads on one socket and 9 threads on the other one, with NUMA-aware optimization, like the data is loaded correctly in each of the sockets to avoid cross-reference as much as possible. In some cases, there is no choice. Nothing changed. However, for Q6, we have a much higher performance. We go to 22 speed up. So it seems a little bit counterintuitive. I think there is some noise in the measurement, but we arbitrarily multiply by 2 the memory bandwidth, right? So Q6 was a query that was actually memory bound, and by using 2 sockets for computation, we end up to have twice more bandwidth to compute, which makes the query go much faster. And we can see that after using 36 core and 72 core, the full machine, we also have a pretty good speed up. So yeah, to come back to there, we could also think that, well, if it's too slow, we may want to add more thread, right? We just add more machine, more thread. But we realize that even if we add more thread for like the last 2 queries, the performance starts to be worse. Like maybe the data is not big enough, or maybe the application do not require more threads. So when we focus on medium-sized data set that can fit in 1 terabyte memory, for example, we just show that Spark is not actually the best, because all the overhead about the RDD, all the overhead about exchanging data between stage is not needed and can be bypassed by using Flare. So Flare removes completely the RDD aspect, because when we run on one single machine, it's actually not that common to have a failure, right? And so now we are going to go to see what happens when we want to use Spark with other machine learning kernel, which is part of the talk today. And so if we use TensorFlow, and so we add an extension to Flare, which we call TensorFlare for now. And so how TensorFlare works is like we have the Flare ecosystem, and we are going to use the TensorFlow runtime. So if you are not familiar with TensorFlow has 2 different modes of operation, or the just-in-time compilation or the ahead-of-time compilation. And so the just-in-time compilation is trying to compile the graph at runtime and do the best it can to compute. But there is also an ahead-of-time compilation that tries to compile the graph as a whole. It's a little bit the same approach that we have done with Spark, but with TensorFlow. And so that's a very good target for our system, because the XLA compiler produces a binary that can be used by other binaries. So what Flare does, it produces one binary that contains the code that we generate for Spark and the code that XLA generate for TensorFlow, and optimize the communication between the two systems. So now we are going to do a demo about that. So again, I'm on another Park and another terminal, because now we are going to do TensorFlare. And I'm going to start PySpark, because TensorFlow is more accessible in Python, and it just shows a little bit how to use Flare using Python. Okay. So same thing here. I have a file when I did my demo, and we are just going to try to use a TensorFlow operation on a in a data frame as a UDF. Okay, so I pre-train the model. So right now it's not about training; it's just about applying it. And so the classifier is so we have just doing a simple regression. We do a matrix vector multiplication, and we access what is the highest probability for that given vector. So we are doing clustering. And so our classifier is just running the TensorFlow application given the 4 parameter the 4 column of the data frame. So yeah, here in the code we have the classifier that is doing that, and we are going to compute a confusion matrix using Spark. And so here, same thing. I'm going to load my demo file. So the data that we are using right now has been generated, and it's composed of 200 points. Okay. So I have a warning about TensorFlow. So here we can do the same thing that we have done with TPCH. So the query. So we create a query, and here we can ask Spark to compute it. So it's a 200 point, and for each of the tuple, we are going to call a TensorFlow code, right? So that's going to introduce a lot of overhead. But it took 10 seconds on 200 points, right? So let's see how better we can do with Flare. So now we cannot just use Flare directly because we need to export the TensorFlow graph into an executable. So first we are going to use tf-compile, which I'm going to show you the code again, of the model. Okay. Yep. So if I go back here, when we were saving the UDF for Spark, we were using the UDF register, but we need to tell Flare about the UDF, right? So what happened for Flare, we call tf-compile, and what we do, we write the graph that has been computed by TensorFlow into a file, and we call the TensorFlare, the tf-compile ahead of time compiler that generate an object file for that model. And so now it has been generated, and if we call Flare on the tensor, we do. So here we have a little bit more compilation time, right? It took 1.4 seconds to compile, so it's a quite big overhead for that small thing. But then it took 90 microseconds to actually do the computation. And with all the overhead to launch the process and go, for TensorFlare, it took 2.1 seconds to execute that query. So it's quite it's still an achievement. And now I'm going to relaunch the code using 2,000 points instead of 200. So that's the same demo, but it's using more data. Okay. And there is I don't know why PySpark do not have a history like Flare. Okay, so first we are going again to use Flare because in that case, Spark is actually going to take a lot of time. So I don't know if you remember. Oh yeah, timing. Sorry. So here you realize I didn't have to call the tf-compile because of the file already been generated. So Flare is going to find again the same model than we saved just the previous run. Thank you. So I don't remember. So it was like 94 milliseconds. So now it took much more time. But overall, the full execution time didn't change much because most of the time is spent in the compilation aspect. Okay. And now I'm going to launch Spark, and that's going to be time for question because it's actually going to take a while. And we'll see if we actually have a result by the end of the question. Thank you very much for your attention.
Yeah, thank you. A very nice talk. What's the intention behind Flare? Is it to go back to the open source, or is it going to be developed as a product, or?
So right now it's more like a research prototype. So we try to apply query compilation, so compilation technique to the database community. I think at one point it's going to be open source and try to actually use real data set stuff, because right now we also do a lot of on example, and we would like to have real life example to make sure that it works on big scale. And so actually I'm going to go back to my presentation. We have a beta program that if you think that this kind of work can be helpful in your work and you want to try to see what kind of optimization we can do on your code, you can contact us, and we will be very happy to be able to improve our system as well on real size data set. So I'm going, yes,
Have you used this for speeding up training?
Right now we don't have for training because there is no batch. We don't have yet a batch support. I think it will actually be quite slow to have it record after record, and also we are a little bit limited by what the XLA compiler can do. So we need, right now it's only support a handful of nodes, and once, I don't think it's actually support training, but don't quote me on that. Last time I checked, it was one of the problems.
So when you mentioned about the runtimes for running in parallel, was it also about running it on different cores?
Yeah, so it was on
the
different
distributed one.
So it was on different cores. So you can ask how many threads you want to use, a little bit like Spark, and then the system is going to use it as efficiently it can. Like if you don't give any information, if it's memory bound or CPU bound, it's going to populate it. If it can fit on one core, it's going to take the first core, and if not, it's going to use two cores. But
so how does it work with multiple workers too? Like on Spark, it has different executors, right?
Yes, so I mean, you could, right now it's a standalone program, but in the future we want to do a kind of a server thing, a server client aspect, so that could be used, because it actually produces a binary that can be run in many processes as possible, if you want to. But right now it's only one at a time.
So this is now similar to how you would run on a driver end?
Yeah.
Yeah, thank you for good talk. So about combining XLA, so if XLA generates a CUDA code, does it work on Flare, TensorFlare?
I don't. Can you repeat
So
that?
if XLA generates a CUDA code for GPU?
No, CUDA code. We don't have a CUDA execution for
only
now.
for CPU for now?
No, we don't.
Only for CPU?
Yeah, only for
Okay,
CPU.
got it, thank you.
So many of those optimizations that you did are quite impressive. Is there like a subset of these that you can foresee being brought back into the main Spark distribution?
So I think one of the easiest one will be to generate code for as much thing as possible, right? Like I talk about for the data loading. I think that one of the things that could be maybe pushed to the furthest, like generating code. One of the things that we remove that will be difficult to remove in general in Spark would be the RDD, right? It's required when you run on multiple cluster. But maybe we can see the RDD more like as a cluster thing rather than when you are on one machine, just revisit the design and make sure that, well, that thing will run as a whole instead of multiple RDD on the same machine.
What compilation techniques do you use? Is there a publication on this or anything? I'm just surprised by the numbers, to be honest. Okay. Is it polyhedral, just data flow analysis?
No, okay, so yeah, so the work is based on the thesis of my advisor. So the compilation framework we're using is called LMS. So it's a multi-stage programming, and when you develop your code, it's actually like if you were writing high-level code, but when you execute the code, instead of producing value, it's actually produce and execute a C-like code that will do the same thing. So it's called a lightweight multi-stage LMS. And if you search for Tiark Rompf, that will be one of the first things that could come along.